In the first video, we took a look at the AMD Programmer's Manual Volume 3, which is our documentation for AMD 64 architecture instructions and what they do. Another important piece of official documentation that's worth looking at is the x86-64 System 5 ABI, or Application Binary Interface. And this specifies how AMD 64 assembly works specifically on 64-bit Linux. So this has things in it like which registers are used for passing arguments to functions, what the return registers are, and etc. So for example, here's the function call sequence section, and this is where it says that the registers that we use to pass arguments to functions are the ones I said they are previously. So let's look through here. So the rules are a little bit complicated, and if you're interested, it's probably worth reading through this just to see what the documentations are, just to see what the documentation looks like. But here's where the rule that I talked about previously is. If an argument is an integer, then the next available register of the sequence RDI, RSI, RDX, RCX, R8, and R9 is used. And in this class, pretty much all of the arguments that we're going to be passing are of class integer, because they're either actual integers or they are pointers, which largely use the same calling convention here. So similarly, if you're looking for where it says that we have to set the AL register to 0 before calling printf, you can find that in here too. The other thing that's worth looking at here is the helper code, or the helper documentation that I've written here for AMD 64 assembly. I've written this cheat sheet to try to help people out, and this goes through the sort of basics of what registers we have, what those registers get used for, what are the common AMD 64 instructions, and quickly how do they work, flow control, memory, what is the sequence for calling a function, which registers do what, how do we write a function, talking about which registers we use for what. We'll get into that more, but that's what these resources here on the page are, and they're worth looking at. Now that we've talked a little bit about that, I want to do a couple more examples. So let me close this out and that. And we don't need this. What we do need is to write a program called ifact for integer factorial. So this is going to be an assembly program, so we're going to start it off the same way we start off all of our assembly programs, with global main. And then I like having my data section first and my text section second, but that's just sort of arbitrary. So we're going to need two strings for this. We're going to need a scan format, because we're going to read a long integer from the user, and we need print format because we're eventually going to print out a long integer. So we're going to say factorial of some number is some other number. Now that we have our string constants, oh, and that needs a new line on it. Now that we have our string constants, we can start on the code. And for iterative factorial, iterative integer factorial, but iterative as opposed to recursive factorial, what we want to do is we want to figure out what our plan is before we start writing code. And so we're going to write out some pseudocode. And the way I like to do pseudocode for assembly is just write like mostly valid C. So we're going to go ahead and declare a variable x. We are going to scanf into x. I need to stop typing semicolons because Emacs does dumb things with them in assembly mode. We're going to specify that a variable y is 1. Then we're going to go from x down to 0, And in that loop, we're going to multiply y times I. Finally, we're going to print out that the factorial of some number is some other number, where the first number that we're printing out is the input x, and then the second number that we're going to print is the output y. So there's our algorithm for calculating a factorial. Now, the next thing that we want to figure out here is, in the C pseudocode, we have names for our variables, and in the assembly code, we have to store these values somewhere, but we don't get to have named variables. So an important thing to figure out is where we're storing things. And it's useful to figure this out before we write any assembly code. Now we have 3 values that we need to store somewhere. We need to allocate places to put them, and those values are the variable x, the variable y, and then the variable ii, which is our loop index. And at this point, usually someone asks me, why do I call my loop index ii? I have a reason for that. Back years ago, I was reading an argument on the internet about how to name variables in computer programs. And you have C programmers who say you should always keep your variable names as short as possible to be concise and save screen space. It makes it so you can see more code at the same time if you have shorter variable names. On the other hand, back then we had Java programmers who said that your variable names should be as long and verbose as possible so that you can immediately, by looking at the variable, understand everything about it. And I tend towards the concise side of that argument, but someone made the important point that single letter variable names, however common they are in mathematics, are especially bad for writing code. And the reason for that is that if you try to search for a variable called I, and we go ahead and do a search for I, it's going to find us the letter I somewhere in the middle of the string. We can make variable names searchable really easily just by doubling them up. So if we call our variable II, then when we search for it, we'll immediately find an instance of that variable. And so that is why I tend to name my variables that would otherwise be single letter variable names, that letter duplicated twice. So that's a distraction. The question that we were trying to do is, where are we putting our values? So we have 3 variables. We have x, the input, y, the output, and I, the loop counter. Now, I we can easily put in some arbitrary register. We'll use RCX. Historically, RCX was actually the loop counter register back in the 8086. It still works for it now, so we're going to go ahead and do that. Y is our output, so we might as well use our output register for it. And you'll note that we have this multiplication here, and you'll further note that the imul instruction tends to use RAX as an implicit output. So not only is that the normal function output, it's also a reasonable output for things like multiplication. RAX, A stands for accumulator, so the intent was that it was used for that sort of thing. And then X is our input, and with our input we have a slight complication. And that complication is that up here in the scanf, we do this address of operation. So the address of operation is a C operator that returns the address in memory where that variable has been allocated. And so far, we haven't been using memory for much of anything. We've been storing values in registers. It's important to remember that registers and memory are 2 completely different places to put things. If something is in a register, then we can't get its memory address because registers aren't memory. If we're going to take the memory address of something, if we're going to have this address of operator be applied to this variable, that means we can't store it in a register. We must store it in memory so that it has a memory address. That raises the question of where in memory do we put it? Last class, we put something in memory by up in our data section, we allocated a sort of global location called num, like this. That's not what we're going to do this time. The other place that we can put stuff is in every function, we have a region of memory that's specific to that call of that function. And this is in an area of memory called the stack. And so we're going to go ahead and allocate x on the stack. And specifically, to find things on the stack, we want to use a register that has a sort of special meaning. That's the register RSP. SP stands for the stack pointer. RSP is one of the 16 registers we have, but it's one of the ones that, in general, as programmers, we don't get to assign it a purpose, because it always has this purpose of containing the memory address, which is at the bottom of the stack. As the stack grows, it grows down, and the stack growing down means that the value in RSP becomes a lower number. RSP goes down as the stack grows. And so we're just going to go ahead and put we're going to put x at the bottom of the stack, and so it's going to be the 8 bytes, because that's how big a long integer is on AMD64, starting at RSP. So we're going to say it's RSP, and the offset from RSP is going to be 0. So that's how we can spell that memory location as an argument to a instruction. So now that we have this much planned, we can start writing our code. Our main function starts at the label main, ends at ret. Traditionally, we'd say enter 0, 0, and then we'd say leave. But we would like to allocate some space on the stack. And one of the things that the enter instruction can do for us is it can allocate space on the stack for local variables. Local variables like this variable x, which we're allocating on the stack. So this first argument to enter is right here, is the number of bytes we want to allocate. So we could conceptually say 8, because that's the amount of space we want to allocate, but we have a problem. We have an alignment requirement for making a function call under AMD64. And so we always want to maintain this alignment invariant. The alignment invariant is that when we call a function, the value in RSP, so the location of the stack, must be aligned at 16 bytes, which means it must be divisible by 16. So when the function was called, we had an aligned stack. It was going to be divisible by 16 when we got into the body of this function. And so when we allocate an amount of memory here with enter, we have to allocate something that's divisible by 16. In this case, a number that's divisible by 16 is 16, so we're going to allocate 16 bytes. We only need 8 bytes, but we're allocating 16 bytes. Continuing onward, now we have to translate this code from our sort of C pseudocode into assembly. And the way we're going to do that is we're going to go ahead and start by calling scanf, because that's the first sort of actual thing that we need to do. Scanf takes 2 arguments. The first argument is that scan format string. So we're going to move that into the first argument register. The second argument is the address of the thing, the address of the bottom of the stack. Now, conveniently for us, the address of the bottom of the stack is stored in RSP, so we could just say move RSP to RSI. That'll do the right thing. But we frequently want to be able to refer to that location as this. So that's going to do the wrong thing. But what if we were wanting to talk about some other offset, like an offset of 8 above the stack pointer? That may have been where we decided to allocate the our x value. And if we had another local variable, we would have to allocate it somewhere else. That's what this number is before the parens. If we have a register, we put it in parens, we're talking about the memory at that address. And if we put a number before it, that's an integer number of bytes offset past the address in the thing. So if this RSP contains the number 1000, this is saying that we want to do a load from memory address 1000 or a store to memory address 1000. But if this were 8, it would say we want to do 1000 plus 8 is 108. So if we want to refer to something in this like load format, there's another instruction called lee, or load effective address, that's going to take a expression in assembly as if we were doing a memory access. It calculates the address where we're going to do the a memory access, but then the thing that ends up in the destination register is the calculated memory address, not the value. So this is another way we can do this, and this this lee is doing exactly the same thing as this mov. We can use either here, but lee is more general, and frequently when you see this address of operator in C code, that's going to translate into this lee instruction in assembly code. So I'm going to leave that lee instruction in. Next we need to mov 0 into AL per the calling convention, then we call scanf, and we're good. Now we need to do the loop. So we're going to move 1 into RAX. That's this line of code here where we set Y as 1, and now we're going to do the loop. So the way a loop works in assembly is we need a label. So if we're going to jump back to the beginning of the loop, we do it by jumping to that label. And then we need a second label for when the loop is complete. So the top label is going to be before we evaluate the condition, at least for a for or while loop. It's the top label is before we evaluate the condition, and the bottom label is when we're done with the loop. So we're going to compare. So we're comparing to 0. That's the 0 is our right-hand argument in our loop condition here. So we're comparing I to 0. I was RCX. We probably also want to move that value at, so we're setting I is equal to X, so we're going to move the value at the memory address RSP plus 0 into our loop counter register. Then we'll compare them, and then we want to continue the loop if I is greater than 0. So we want to exit the loop if I is less than or equal to 0. So the condition in the C code is asking, do we want to continue the loop? The condition that we're translating it into in the assembly is asking, when do we want to exit the loop? And we want to exit the loop when I is less than or equal to 0. So that's our loop condition. Now we're going to have our loop body. Our loop body here is just imul RCX. So this is y equals y times I, because y is in RAX, and RAX is the implicit first argument and destination of imul. This also clobbers our dx because multiplication produces a 128-bit value, and the top 64 bits, which in this case will always be 0, ends up in there. So then after that, we want to decrement. We're decrementing our loop counter, and then we will unconditionally jump back up to the loop condition to check it again to see if we're continuing the loop. Loop done is our sort of closed curly bracket up here. This closed curly bracket, and then all we have to do is this printf. So we're going to mov print format into RDI. We're going to mov RAX into RSI. We're going to mov 0 into AL. But actually, our print format has two things, and we want to move our X into RSI. So the third one is RDX. Mov 0 RSP into RDSI. Call printf. It looks like we want to return 0 from our main function because we are executing successfully. And so there's our complete source code for our iterative factorial program. We're doing factorial in a loop. Let's see if it works. No pi o ifact.s. First try. This really is the first take, as you can tell by all the times I stumbled talking about the documentation. Ifact. So it wants me to enter a number. What's factorial of 1 is 1. Factorial of 2 is 2. Factorial of 3 is 6. Factorial of 5 is 120. That's the number we expect. So our first attempt at factorial worked. So that was fun. But whenever we're talking about factorial in computer science, obviously we want to do it recursively. So that's going to be our next example, is we're going to go through and do recursive factorial. And to do that, I need to force this thing to not cache so I can load a web page. There we go. So if iterative factorial is called ifact, then recursive factorial is called rfact. So again, global main, again, data, then text. Again, our data is going to contain two strings, our scan format and our print format, exactly the same as the iterative factorial version. And then we want pseudocode. So we're going to have a main function, and in the main function we are going to say long x scanf into x, long y is fact of x, and then printf fact ld is ld x y. So that's exciting. And in fact, I'm going to go ahead and copy that logic over from the main function in the other version, because that's all exactly the same. So we still want to allocate 8 bytes here. We still are going to scanf into x. We don't need our loop condition. We're going to call fact mov 0 RSP into RDI, because that's our first argument for that factorial function. We don't need to know anything about the factorial function to call it. That's the point of the calling convention, is the factorial function is going to follow the conventions. So we just have to put a value in RDI, call fact, and then it will put the result in RAX, which is where we want it. So we already have our code completed for main. The interesting question is, what does our code for fact look like? So this is going to say If x is less than or equal to 1, return 1. Otherwise, we're going to return x times factorial of x minus 1. So that should be pretty easy. Yeah, fact. Enter 0, 0, leave ret. So I guess for now, x is RDI, because that's where it's going to come in. And yeah, that's all we need to do. So we're going to compare. We need to compare 1 to RDI. And if 1 is less than or equal to the value in RDI, we're going to jump to fact done. We need to return 1 in that case, and I'm going to do a little trick. I'm going to move 1 to RAX up here. If we jump to fact done, then RAX doesn't get set anywhere else, and so we end up returning 1. If we don't jump here, then whatever code here gets to set RAX however it wants, and so it might be a like excess mov that happened here, but individual instructions are cheap, so this is just an easy way to write the code. Next thing that we want to do is we're going to go ahead and say that we're going to decrement RDI, because we want to calculate x minus 1, and then we'll call fact. After we do this, RAX will contain the value of factorial of x minus 1. And then the next thing that we need to do is call imul on RDI. So that's going to multiply RAX, which was x minus 1, times RDI, which according to this is x. Then imul puts the result back in RAX, and so it looks like this should produce the correct value. Quick question before I try it. Do you think this is going to work, or do you think it's going to break? If it breaks, is it going to be because I typoed something, or because there's a logic error? If you think it's a typo, where's the typo? If you think it's a logic error, what's the logic error? Let's give this a try. rfact, no pi. rfact.s. So we'll try 5, and it turns out that factorial of 5 is 1. Well, we wanted factorial of 5 to be 120, so that's not the answer that we wanted. So think for a second. Our main code we copied directly from the version that worked with the loop, so probably the error is somewhere in the factorial function. What's the problem? All right, let's walk through how this works. If we call factorial of 2, we still get 1. So if we call factorial of 2, at this point, RDI contains 2. We're going to move 1 to RAX. We're going to compare RDI to 1. RDI is 2, so we do not jump. Then we decrement RDI. RDI is 1. Then we're going to call factorial. Factorial is going to come back here, and we're going to do this again with x is 1. X is 1 means the comparison less than or equal to 2 succeeds, so the recursive call is going to return 1. So down here, factorial returns 1. We multiply that with the value in RDI, which was decremented. It had been 2, but we decremented it to 1. Wait, no, it's worse than that. It's whatever the value was in the inner function. So we had definitely decremented it. And in this case, we know that it didn't change in the recursive call, because the recursive call was the base case, which doesn't set the value of RDI. But in any case, it's 1. So we multiply 1 by 1, and it's 1. If we go through this again with 3, we'll see that we're multiplying 1 times 1 times 1, which is still 1. The problem is, when we decrement RDI here, that means that we no longer have the original value x. So before I decrement RDI, let's go ahead and save it. Mov RDI into R8. And then before we multiply, we're going to mov R8 back to RDI. So now if we do rfact of 1, we get the right answer 1. Rfact of 2, we get the right answer 2. Rfact of 3, we get 4. Now, factorial of 3 is 6, but we get 4. Think for a moment, why does this not work? So the answer is that we only saved one value of RDI. And the problem with this sort of recursive structure is that there's only one RDI register in the processor, but every recursive call wants a different value of X. And so once we end up with more than two calls, more than one recursive call, these X's start overwriting each other, even though we're backing up one copy to another register. So we don't need to just be able to back up one copy, we need to be able to back up an unlimited number of copies. So we've seen one way to do that, and the way to do that is to allocate space on the stack. Rather than having X be RDI, we're going to have X be 0, well, we'll have X be 8 RSP. We have to allocate 16 bytes for stack alignment. So what we're going to do here is we're going to move RDI over to 8 RSP. Then we're going to move 8 RSP back to RDI. And now, every time we call the function, enter allocates another 8 bytes on the stack grows down. And so now if we call rfact 5, we get 120. So that's one option for avoiding this problem of having a register get overwritten by a value when we do a recursive call. There's a couple other solutions. One solution is to use safe registers. Actually, let's do the temporary register solution first. So one of the things about the calling convention, let me go ahead and bring up our notes. If you go look at that calling convention document, we have two different kinds of registers that we're worried about here. We have 16 total registers. I'm going to ignore that package I just got for a second. We have 16 total registers. Actually, I'm going to pause this. I'll be back. All right, that was definitely the DHL guy, but yeah, we have 16 total registers. So those registers are RDI, RSI, RCX, RDX, RAX, RBX. So we have A, B, C, D, S, I, D, I, RBP, RSP, R8, R9, R10, R11, R12, R13, R14, and R15. And these are split by the application binary interface into two categories. And I call these two categories temporary registers and safe registers. So they're split up kind of arbitrarily. The temporary registers are, let me pull up this thing just to make sure that I'm getting it right. The temporary registers are RDI, RSI, RDX, RCX, R8, and R9. You'll recognize those as being the function call register, the function call argument registers. The argument registers are all temporary registers. We have our AX, R8, and RAX, R10, and R11. Now the rule with temporary registers, if you call a function or a system call, though these registers are assumed to be overwritten. And what that means is if you want to have a value in the register, then you are responsible for preserving that value across function calls. That's called callee save. So this is a pattern that we can follow in order to save a register across a function call. The other possibility is to use one of the other registers, which I call safe registers. Those are R12, R13, R14, R15, and RBX. Now, technically, RBP and RSP count as safe registers, but they are registers that we want to use because they're sort of reserved for managing stack addresses. So we're just going to ignore those for the moment. And the rule with safe registers if you have a value in one of these registers and you call a function, then when that function returns, the value you left there will still be there. But that means that if you use these registers, you must save the previous value and restore it before returning. So the function that if you use these registers, you are responsible for restoring them to whatever state they were in when you found them. And these are called caller backwards. These are called callee save. These are called caller save. So the function that calls another function has to save the temporary register. The function that is called, the callee, has to save a safe register. So these are two more ways that we can avoid having registers get overwritten on function calls. Let's go ahead and try out both of them on a recursive factorial. Not that one. Recursive factorial. So what we're going to do is, so this is just allocating on the stack. Which I'm going to say is not our first plan. It might not be our last plan, but it's not our first plan. Plan A is use a safe register. Plan B is use a temporary. So if we're going to use a temporary register, that means we're going to have, we're going to be pushing values onto the stack. So we're going to allocate 8 bytes on the stack. Stack is now unaligned. Then we are going to push RDI here. Then down here, we're going to pop RDI. Now push and pop, what they do is they move the stack down by the size of a register, put the value from that register onto the stack. That's push. Pop takes the value at the bottom of the stack, puts it in a register, and then moves the stack back up. And the requirement for stack alignment is that when we do a function call, the stack must be aligned. So the fact that we unalign the stack here and then realign it here is okay. That's allowed. So before we call another function, we're preserving the value in RDI because RDI is a temporary register. And so if we want that value to survive across the function call, we, the caller, are responsible for saving it. And then when we go ahead and build this, and call rfact and type in 5, it does the right thing. That's not a very exciting demo because we got exactly the same behavior as we got from the last thing, but this is one of the ways to avoid having our variable values get clobbered. All right, plan A is use a safe register. This is the simplest pattern to follow. It's a little bit, it sort of seems like the most complicated way to do it, but if you consistently follow the pattern, it gives you the least chance of messing up. It's easiest to see that you did things correctly. So we're going to take out the push and pop here, and what we're going to do is we're going to say that X is R12, which is a safe register, and then we're going to push R12, then we're going to pop R12. So the rule for a safe register is that we, as the callee, if we're using the register at all, we're responsible for saving the register before we touch its value, and then restoring its value before we return. Pushing is going to move the stack by 8, which is going to make the stack unaligned. Entering by 8 restores the stack alignment. And as long as we keep push outside enter and pop outside leave, that will work. If we put the push and pop inside the enter and leave, that will also work, but the convention that I want you to follow for this class is to put your pushes of safe registers and pops of safe registers between label and enter up here, and then put the pops between leave and ret down here. Each push moves the stack by 8. So if we have an odd number of pushes, we need to enter 8. If we have an even number of pushes, we have to enter 0. We could enter some larger number. This could be enter 24. And then we'd be allocating 16 in addition to the 8 for stack alignment. But here we're just going to enter 8. Compile, enter 5. Factorial of 5 is 1. I got something wrong. Let's see what I got wrong. The thing that I got wrong is that we're not actually using R12. So we need to mov RDI into R12 here once we actually have, in fact, yeah, we're going to move RDI to R12 here, and then we're going to do our imul by R12 since that's the value for X that we want. Then we do 5 and we get the right answer. All right, so that is a recursive function, recursive implementation of factorial. That is the problem that we run into when we aren't careful about reusing registers across function calls. That is the convention for register use with function calls according to the AMD64 System 5 calling convention, where we have temporary and safe registers. And that is the sort of 3 solutions that we have for getting it all to work by using those conventions. So I'll be back in a second with some more information on what the stack looks like.